Hello everyone, Lloyd Rieber here again with my next Q workshop video. Well, at this point you've conducted your first Q sort and you have data in hand. Congratulations. Now you have to figure out what to do with it. The first step in a Q analysis is to determine how many distinct viewpoints exist among the Q sorts you've collected. In order to determine this, we're going to run something called a factor analysis. A factor analysis is often described as a data reduction technique. That means that although you may have 15, 20, or 30 Q sorts in your P set, it is almost certain that the number of shared viewpoints is much smaller. The number of distinct viewpoints will probably land somewhere between 2 and 6. To do this, the factor analysis looks at all of the data to detect similarities between all of the Q sorts based on correlations of the Q sorts. An important point to keep in mind is that there can be many legitimate factor solutions. In fact, the process to determine the best factor solution is yet another qualitative judgment the researcher has to make. So don't be unnerved by this ambiguous element of factor analysis, but accept it as a part of your skill development within Q. This presentation is based on Chapter 5 of the book by Simon Watts and Paul Stanner titled Understanding the Analytic Process 1, Factor Extraction. As the one in the title suggests, we are breaking up the analytic process into two parts. This chapter and this video will focus on factor extraction. The next chapter will focus on something called factor rotation. Okay, let's start by going over some key concepts and principles of factor extraction. Factor analysis involves a statistical procedure, so we have to face the fact that we're going to have to deal with learning some statistics. Now, fortunately, we have software packages that are going to do the heavy lifting for us. But I do think it's important to get a good basic understanding of the fundamentals of the statistics involved in factor analysis. And to me, that involves understanding what we really mean by correlation. So I am not a statistician, but I am an educational researcher who has been using statistics for really about 40 years. So I'm very comfortable with statistics. I understand my limits in understanding, and I'm a very practical person. I want to make sure I know enough about the statistics I'm going to use in order to use them appropriately. So I would recommend to everyone to watch a couple of videos that I've made that explains what exactly a correlation is from the basis of doing the calculations. But I use a very standard and a long-standing learning principle that you start with what people know. You go from the known to the unknown. You build bridges from the known to the unknown. So in these two videos that I recommend you watch, I start off with what we all know. That is, what is a single number all about? And I move up through averages, standard deviations, z-scores, which are incredibly important and also extremely fascinating. And those become the basis for correlation. So I really recommend you take some time to watch those videos and get a grasp of what it means by understanding correlation. And this idea too of z-scores, I just think they're fascinating. They're just awesome. And if you want to cut to the quick of trying to understand what z-scores are in some more detail, you might want to check out my series of videos related to my MOOC called Statistics in Education for Mere Mortals. And you can see my dog Sunny, who can help us understand z-scores through a fictional account of him failing miserably in obedience school. So check it out and you'll be better off for it. So yes, correlations really are the raw material for a factor analysis. And here is a standard correlation matrix that I found related to a Q sort I did a while ago. And you can kind of see all the people, all the names going down in column A, but you also see their names at the top as a header in row 4. So, you know, JH, a correlation with yourself is always going to be 100. It's a perfect correlation. So you see the 100s going down the diagonal. But it is really important to do a little inspection of the correlation matrix because it kind of gives you some hints as to what's going on in the data. For example, you can see how JH has a rather high correlation with Amy and Lona, but pretty small, almost near zero correlation, with AJ. So you get a sense of uh, who JH is, his responses are similar to, and whose they are not. Now, we might notice some other patterns like this through an eyeball inspection, but what a factor analysis really involves is a statistical inspection of the correlation matrix. And so it is doing a similar inspection by using mathematics to really find those distinct regularities or patterns of similarity in the correlation matrix. I am always a sucker for good analogies and good metaphors, and the Watson Stenner book really has I think, a really good analogy that uh, doing a factor analysis is like baking a cake and trying to decide how to cut the cake. And so, using their analogy, Q sorts are going to be like the ingredients for the cake. The correlation matrix is the cake. And again, the factors are the slices of the cake. And the big decision for factor analysis, to use the analogy, is how many slices, or how should I slice the cake? And it sounds like a silly question. How many possible ways are there to slice a cake? Well, it's kind of infinite. There may be lots of solutions. Maybe there's only two people who want to eat that cake, but it's a very small cake, and so half of the cake makes sense. But with more of a regular sized cake, you might be thinking about the cake itself. And I think this little photograph of a cake with those little chocolate flowers on the top kind of give you an idea that I might want to slice that cake so that you get one of those little chocolate flowers on each particular slice. So there is definitely going to be a qualitative approach to making that decision of how many slices we want to cut our cake into. So, as the quote says, in each and every Q analysis, therefore, we are just trying to find a preferable way to cut the cake. There are two main approaches to doing factor analysis that you will read in the literature. One is exploratory factor analysis, and the other is confirmatory factor analysis. And for most of the Q work that I've seen, it's really exploratory factor analysis that makes the most sense. If you had a very definite theory you were building and you wanted to conduct a Q sort in order to test that theory, then you would be stepping your toes into the world of confirmatory factor analysis. But I really like the quote that Watson Stenner used from Stevenson on page 96, that he says that we should begin each new analysis with a fresh and puzzled attitude, believing nothing and expecting little. So we allow ourselves to let the data tell us how we should cut the cake. We are looking for those individuals who are in the Q sort itself and their responses via their Q sorts to kind of tell us what's going on. What are the viewpoints that they are trying to express? So really, we are trying to find out or make sense out of the differences in all of those Q sorts. If everybody who did the Q sort did exactly the same thing, there would be really nothing to analyze. There would be one completely perfect view that everybody had, but that never happens. So what we're looking for are those differences and trying to understand them. When we talk about differences, what we're really talking about in statistical terms is variance. And the total variance, all of the differences, can be separated into three main parts: common variance, specific variance, and error variance. And you will typically see variance talked about with a pie chart. And it really is looking at the area of each of one of these types of variance. And I always like to think in terms of squares instead of circles, because it's easier for me to think of area with squares, because, or a rectangle, it's just one side times the other gives me the area. And you might be saying, well, why area? Well, again, it's going to be like an amount of difference or variance. And so what we do is you will see a lot of squaring of numbers in the statistics. If I take a standard deviation and square it, I get the variance. Now you might be saying, why do we square numbers to get the variance? Well, let me ask you, how much space does a line take up? So you need to have two-dimensional space for us to make sense out of area. So you can see here, I just randomly kind of color coded this, where we're looking to find what is the common variance, or really are the differences among the group as it pertains to the topics or the viewpoints that are there. But we also have two other types of variance. One is called specific variance, and the other is called error variance. I've never really found a good explanation of what specific variance is, so I actually looked up a definition from the APA dictionary. But as far as I can tell, it's kind of like the quirkiness that kind of every person's responses kind of contains. It doesn't really apply to the entire group, and it's not related to error variance, which I'll talk about in just a second. So it's just sort of this really quirky type of other variance that kind of exists. But let's talk about error variance. Error variance refers to the imperfections or flaws that occur when you conduct a study. And there's never a perfect study, but error variance can be something that the researcher can try to minimize. Many times, error variance results from a poorly designed study. And I think a really good example of this might be how we might design our Q sort statements. We already talked about how, for example, we want to avoid double-barreled statements or statements with the negative phrasing of it, because it can confuse the participant, and they get confused, then they sort a statement, but it doesn't really represent what their viewpoint is. Here's a kind of a classic example, more from a typical R survey, where we would write or a test, like we're putting together some sort of a performance test. So, for example, if I said, especially in a timed test situation, answer this question, I said Bob has 5 cookies and Jim has 4 cookies. After Bob gives Jim 2 more cookies, how many does he have? And since I'm in a hurry, I might very quickly say 6, because I'm thinking about Jim. But the interesting thing is the researcher might have been thinking about Bob as being the correct answer. Then that would be a 3. The trouble here, of course, is that the pronoun he is an indefinite pronoun. It doesn't clearly tell me, am I referring to Bob or to Jim? So you could have a great example of a person who knows the answer, but yet gets scored incorrectly. That would contribute mightily to error variance. So obviously we want to reduce error variance as much as we can. And one of the best ways we can do that is to have a very carefully designed research study. Now, there are a variety of statistical techniques for doing this data reduction task. One is actually called factor analysis. But in the remainder of this video, we will focus on a technique called principal components analysis, or PCA. And you can think of a component as analogous to a factor. Another common technique in the Q world is centroid analysis. And again, a centroid is also analogous to a factor. There's other techniques as well. One I know of called cluster analysis, although I don't know much about it, to be honest with you. But all that said, I'll be using the term factor analysis in a generic sense to refer generally to the concept of data reduction. And it is worth mentioning something about the software packages that are available for doing a Q analysis. And yes, you can use SPSS. This is the standard statistical package that you will find for the social sciences that is out there to do factor analysis. It obviously does factor analysis, but you'd have to do some gymnastics in order to get it to actually work with Q. Plus, it would not give you the kind of output that you would want for your interpretation, namely a factor array. The one software package that you will hear mostly about is PQ method. In fact, the chapter in Watson Stenner gives a lot of coverage and attention to it. And for years and years, it was the standard package to use. And you will still find Q scholars using it all over the world. And you just have to give some recognition and admiration to the developers. Another one is PCQ for Windows by Michael Strickland. And I actually met Dr. Strickland at my first Q conference. He was such a nice fellow. He was really went out of his way to talk to everybody who he saw was new to the Q conference. So I really appreciate that. He passed away a short time ago. But I'll be focusing on KenQ, which I've been, of course, focusing on in my past videos. And again, I give a lot of credit and admiration to Sean Banaszak for making it available to us all for free. And it is going to be the package I'm going to recommend everybody. Again, I tend to use the desktop edition called CADE. In the remainder of this video, I'll demonstrate briefly an example of factor extraction using a Q-sort I did a while back on the topic of the role of government in American economics. And so here's an example of the Q set. You can read those if you want, if you're interested in the topic. Let's take a look at the correlations. And you can kind of see there a variety of negative correlation that those kind of pop out at you in red. But again, I could take a visual inspection to take a look at these to see where are some of the highest correlations or where are some of the near zero correlations. So I see 63 and 60, and I see 1, 0. So there's definitely a lot of variation here. But let's take a look now at the factors. So we're going to use, again, principal components as our way to do data reduction. So I'll click on principal components. And in the truly blink of an eye, KenQ has done the math. And as I scroll down now, we will see it does it automatically for 8 factors. And I scroll down and I can see the eigenvalues for all of those factors. So I think the main point is that if you know what the eigenvalue is, you also know something about the amount of shared or common variance in each of the factors. And you can see that it starts at 9.87, then 5.4. In fact, they're all above 1. And you may recall that we have a basic rule of thumb called the Kaiser-Gutman criterion, that if the eigenvalue is greater than 1, we should keep the factor. So according to this, I should keep all of the factors. But we have another way of looking at the decision, and that is with the scree plot. And it's interesting with the scree plot. It's just exactly the same numbers again. So 9.87, that's what that dot right there is, and I go all the way down to factor 8, 1.16. You can see that down here. So it's no more than a visual representation of the eigenvalues. And you may recall that if we use a scree plot, we would try to find where the slope changes, and we would only use the factors that would be related to the first of those slopes, because again, the rest of it would be considered the scree. Remember the analogy to a mountain and all the debris that falls off. What here is actually attached yet to the mountain. And according to this, I would say factors 1, 2, and 3 are going to be those factors, with the rest being the scree. And you can kind of see also up here, if we start to do the cumulative explained variance, so 31, and then 31 plus 17 is 48, 48 plus 8 is 56. You can see how those numbers are going, they're very, very small as I go down. And there is a kind of a rule of thumb that anything above about 35 to 40% really would be considered a pretty sound solution. So you can see that once we get above factor 3, we're not really getting too much more in terms of the common variance. But again, this is an open decision. So how do we decide? Well, I think first we think about what our research questions are. Are we really trying to extract every single viewpoint that exists, even if the differences between the viewpoints are very, very minor? And that's where you'll hear Stephen Brown talk about spurious factors or spurious viewpoints, where the viewpoint, for all practical purposes, isn't adding anything new if I just keep adding another viewpoint and another viewpoint, even though the eigenvalue is over 1. So, but the beauty of KenQ is I can just try it out. So let's go ahead and do a rotation using all 8 of the factors. So let me go ahead and submit that. And rotation is going to be the next topic of the next video in the next chapter. But I find in order to be able to talk about factor extraction, you have to be able to play with the data, which KenQ allows me to do. And you have to kind of go through the rotation aspect here. So we'll talk more about rotation next time. But I'm going to use Varimax rotation for the purposes of this video. And I'm now, okay, it worked, Varimax applied. I'm going to go to loadings, and I just love how KenQ gives me the colors, and then I can auto flag. So I can see that, yeah, it shows that I have these 8 factors. In fact, I have to scroll over. And you can see how factors 7 and 8, there's only one Q sort loading on each of those 2 factors. And there's that other rule of thumb that says you have to have at least 2 Q sorts loading on a factor for it to be a meaningful factor. So but you also notice too how many people are not significantly loading on any one of those factors. I should say their Q sorts are not loading significantly on any one of those factors. And that's not really part of my research question, because I really wanted to have as many of the students in this class be represented to have their voices represented. So look at all the people down here that, again, aren't even represented. So I'm not really too happy with this solution, and this kind of starts to tell me that the scree plot might be a better solution. So no problem. I can go back to step number 4, factors, and reset the analysis. Yeah. So let's just do it again, principal components. This is exactly the same data I had before, same scree plot. I'm now going to go to rotation. This time I'm going to, again, I could try 7 or 6 and see how that goes, or 5, but I'm going to go now to the scree plot, giving me the advice of trying 3. So let me choose 3, submit that, go to Varimax rotation, click it, it's applied. Now go to the loadings. And this looks cleaner to me. It gives me a sense of 3 really main viewpoints that are jumping out at me. And as you can see also, there's only 2 people whose Q sorts are not loading significantly on any one of those factors. And this is rather common, by the way. You can see this rye here, 0.53, 0.59, 0.33. These are, again, correlations. This person has something in common. Their viewpoint, I should say, has something in common with all 3 of the viewpoints, and it's pretty evenly split between the first two factors. And Vinny here, the same thing, but on factors 2 and 3. So I would say this would be a much better solution. And again, I would continue perhaps playing around with it. One other thing I want to point out, which is kind of interesting that it happened to be the case here, you might notice that Sam and Hannah have a negative correlation, a pretty highly significant correlation, a negative correlation with factor 1. What does that mean? Well, in essence, it means that whatever the factor 1 viewpoint is, they basically have a mirror image or opposite view of that particular viewpoint. And what I really like about KenQ is I can split factors like that. That's called a bipolar. There's 2 poles, and I can split that factor into 2. So I'm going to click that. Which factor to split? Well, number 1, that's what I'm looking at. So now I have 4 factors, but you notice that it's really factor 1A, factor 1B. So I would interpret factor 1A first, and then talk about factor 1B as again being the opposite, and then factors 2 and 3. So yes, we have to accept that decisions about how many factors to keep will involve some ambiguity and vagueness. We do have some general guidelines to follow that will help us, but in the end, we, the researchers, will need to make a decision based on our research questions and the nature of the data. There is a certain amount of trial and error as we try out different solutions to see how well they fit. Fortunately, KenQ makes it easy to do this. And don't be surprised that maybe later, when you're actually struggling with interpreting the meaning of each factor, that you may decide then that you need to come back to KenQ and try out yet other possible solutions based on hints, hunches, or insights you're gathering along the way. Okay, that's it. Until next time.